Good afternoon, dear students. Let's start our lecture. So today we are going to talk about the heteroscedasticity problem. And generally speaking, we continue our discussion about the problems that researchers face when they conduct the regression analysis. The kind of these problems I want to put the word problems in quotes in this context when I talk about the multicollinearity, the problem that we discussed previous time, and the problem of heteroscedasticity, the topic of our discussion today, because in most cases, such kind of problems could be relatively easily solved. What you should do, you should just be ready and be able to solve them. And next time we are going to discuss the problem of endogeneity, and such kind of problem could not be so relatively be solved as multicollinearity and heteroscedasticity. And in most cases, the problem of endogeneity, when we face this problem, we need to change the assessment method or change the model, or sometimes we should change our data and so on. So anyway, you should remember that if you ignore the problem, you can obtain wrong hypothesis tests or wrong conclusion about the significance of your results, and of course your conclusion of all your empirical research will be wrong. So this is our plan for today. Most of the time we are going to discuss the problem of heteroscedasticity, and in the end of our lecture we are going to discuss the new kind for us new kind of variable. We discuss the interaction variables in the context of functional form of our models. Why do we need such kind of interactions, and how can we interpret them? Okay, so I will always remind you about the ordinal least square assumptions. This is really very important, and we have already discussed this slide in the previous lecture when we discussed the problem of multicollinearity and when we distinguish two definitions. A perfect collinearity, you can see this assumption, no perfect collinearity assumption among the basic assumptions of Gauss-Markov theorem. And I hope that you understand the difference between perfect collinearity and multicollinearity. So now let's take a look at the fifth assumption here is homoscedasticity, and you can notice that the minimal requirement of our estimator coefficients that they should be consistent and unbiased. And for this purpose, you should hold these first four assumptions about the linearity, about the random sample from the population, about no perfect linearity, and of course zero conditional mean assumption. But homoscedasticity is also the requirement if we talk about the Gauss-Markov theorem, because if you want to obtain best linear unbiased estimators, you need to hold all of these assumptions. So you can conclude, even from this slide, that heteroscedasticity problem in the situation when you fail to hold the homoscedasticity doesn't lead to unbiased or inconsistency of your estimators. So even if you notice the problem of heteroscedasticity, for example, yeah, even in this case, you have a chance that your estimators will be unbiased and consistent. Of course, if you hold all other assumptions. But the problem is that your estimator will not be efficient. Efficient means have the lowest variance among all other unbiased and consistent estimators. And also you can notice from this slide, and maybe previously you should remember that the properties of your estimators of the regression coefficient depend on the properties of the disturbance term in your regression model. This is very important because today all our discussion about the homoscedasticity will be around the error term or around the disturbance term. Okay? Sorry, could you hear me? I have some message from the Microsoft Teams that some problem with the internet connection, or it's okay?
Yes, it's okay.
Okay. So let's continue. First of all, let's start with some general definition of homoscedasticity. I hope that you know this definition from our fourth lecture, where we discussed the Gauss-Markov assumptions and the Gauss-Markov theorem. But anyway, let's recall this definition. So the Gauss-Markov conditions listed in the previous slide states that the variance of the disturbance term in each observation should be constant. So it means that the error had the same variance given any value of your axis. Mathematically, you can write this as following. So it means that the variance in the error term conditional on other explanatory variables is the same for all combination of outcomes of the explanatory variables. Or in other words, it equals some constant. For example, if you have model of wage on education level, let's say in years, for example, on the experience and on the tenure, homoscedasticity requires that the variance of the unobserved error doesn't depend on the levels of these explanatory variables: education, experience, tenure. So if you rewrite this general formula for this example, you can rewrite this as following. So variance of your error term conditional on education, experience, tenure equals some positive constant value. And let's illustrate this in some graph, how it looks like. So for the sake of simplicity, we have some sample, and for the sake of simplicity, we have here only 5 observations, very, very small sample. So let's start with the first observation, x1. If there were no disturbance term in the model, the observation would be represented by the circle on the line, on this line. Here's the sample regression line. Of course, if we talk about the heteroscedasticity problem, we can talk in the context of simple regression model also. Yeah. And you can notice that the effect of this disturbance term is to shift your observation upwards or let's say, as in this example, downwards vertically. So the potential distribution of the disturbance term before the observation has been generated could be presented like a normal distribution centered on this circle. But the actual value of the disturbance term for this observation, this one, turned out to be negative. So the observation being represented here, represented by the solid marker, this one. And the potential distribution of disturbance term and the actual atom are shown in similar way for all other observations. So this is the picture of homoscedasticity. But of course, homoscedasticity fails whenever the variance of the unobserved factors changes around different segments of the population. So when I talk about the different segments of population, I mean that these segments are defined by different variables of X, different independent variables. So heteroscedasticity arises in different error terms that don't have identical variances. So if you translate literal homoscedasticity, homo means equal, as skedasticity means dis disturbance. So heteroscedasticity is an opposite situation. And also I want to know that in some sources you can find this the spelling of this word through C, and in other sources you can find the spelling of this word from K, like in this case. So don't be confused. This doesn't mean that you see some typo in some book, for example. Both spellings are correct, both spellings are valid. So let's provide some examples about the heteroscedasticity problem. Let's say that in our sample we have different groups of respondents. For example, we have males, or and also we have females, and we can assume with the high probability that they have different variances. For example, in income, or for example, in the health status or some other indicators. So it can be expected that the variation of unexplained household savings increases with income. It's logical, yeah? As well as the level of savings will increase also with the income. And one more example, how can you suppose that you have the problem of heteroscedasticity? That, for example, you can expect that the variation in food expenditures among high-income households is much larger than the variation among low-income households. It's always logical in the general sense, yeah? But the problem is how it looks like, first of all, of course. We continue the same example where we have again we have the same 5 observations, and again we discuss the problem of heteroscedasticity on the example of simple regression model. But now if you compare the previous pictures with this one, you can notice that now variance of the disturbance term is increasing as x increases in this example, yeah? But of course, this doesn't mean that the disturbance term will be necessarily have a particularly large value in observation where x is large. But it means that the probability of having an erratic value will be relatively high in this case. So this is one of the example how heteroskedasticity can looks like. So here you can see some pattern. Um, so what is the problem? Why does heteroskedasticity matter? So what are the consequences? First of all, if you return to the first slide with the ordinal least square assumptions, and again take a look on the slide, you can find again that your estimator of coefficient will be not will necessarily will be, but uh, you have a chance that your coefficient will be unbiased and consistent. But again, the problem as in the multicollinearity example, the problem will be with the variance of your coefficients or with the standard errors of your coefficients. So the key point that you want your variance will be as small as possible. So in the probabilistic sense, it means that you obtain the coefficients with the maximum precision. And if there is no heteroskedasticity and if all other ordinal least square assumptions are satisfied, the regression coefficients have the lowest variance of all the unbiased estimated that are linear functions of your observations of dependent variable. But if the heteroskedasticity is present in your data, the ordinal least squares estimators are inefficient. Inefficient because you could at least in principle find other estimators that have smaller variance, but they still be unbiased and consistent. And because of this, generally speaking, all as estimated are not blue. And also we will have some problem with our t statistic, with f distribution, so we can check the significance of our model in general, and we cannot check the significance of partial effects of our coefficients. But I want to add to the first point that your coefficient will be unbiased, and also you can use R squared and adjusted R squared indicators, because R squared and adjusted R squared indicated will be also unaffected by the presence of heteroskedasticity in your model, because the key point that they will be unaffected because population R squared are unconditional variance, and because of this population R squared will be unaffected. So now let's discuss the causes or the reasons of heteroskedasticity in your data, and possible reasons. The first common and the first reason why heteroskedasticity in most of the samples, generally speaking, is a rule than not the in most situations, because heteroskedasticity is likely to be a problem when the values of variables in the sample vary substantially in different observations. For example, you have a sample of different companies and you have very small, medium, and large companies in your sample. And you want to find the relationship between, for example, the income and some other characteristics of the firms, and you can assume that firms who has larger income and, for example, who has the high value of employees Of course, the variance in that firm will be higher if we compare with the small companies. So the reasonable explanation why it works in this way, because the variation in the emitted variables and the measurement errors, and you should remember, yeah, that emitted variable and measurement errors are jointly responsible for the disturbance term. They will be relatively small when your dependent and when your independent variables are small. And of course, the problem of emitted variable and the problem of measurement error will be large when when you have large values of x or large values of y. So let's take a look at another example. Let's say that you work with the sample of different countries and you want to find the effect of value added in manufacturing on gross domestic product. So if you know that in your sample you have small economies, let's say like Slovenia, and huge countries, I mean huge economies, yeah, when I say the word countries, like United Kingdom or let's say the United States of America, of course you can assume that the variance in gross domestic products as well as in the value added manufacturing will be higher in large countries if you compare with the countries with the small economy. The second reason that of course heteroscedasticity can arise when you have the outliers in your sample. And you should remember, yeah, that outlier is some observation that is much different in relation to the observation in the sample, to the rest observations in your sample. Generally speaking, outlier is some observation that comes from other population. So in this case, again, you can assume if you find outliers in your sample, you can assume that you have the problem of heteroscedasticity. That will be your preliminary conclusion before you check this. Also, skewness in the distribution of your variable in your regressors could arise the heteroscedasticity problem, or incorrect data transformation, or also if you have the incorrect form of your model. For example, you run the linear regression model, but instead of this, you need to run log lean or lean log or log log model and so on. So all these problems are frequently arises in the cross-sectional data and also in the panel data. But for example, if you compare with the time series data, in time series data, you work with the general the same variable, but you check the dynamic of this variable in different periods. So you, for example, follow the same indicator, let's say GDP, during some long period. Yeah. And in this case, the size of this indicator will be almost the same in each period. But for the cross-sectional data and for the panel data, heteroscedasticity is very, very common problem. Okay, so the main question, okay, we assume that we have, in most cases, we have a problem of heteroscedasticity. Maybe it's not very complicated problem for our solution, but anyway, we need to solve this problem. But before this, we need to check with some methods if we really can assume that we have this problem. And in principle, there is no limit to the possible different types of heteroscedasticity. And accordingly to large number of different tests appropriate for different circumstances have been proposed. But we are going to discuss only two of them. You can find different tests, more different tests in books, maybe in other sources. But we are going to talk about only two of them that are very popular. And all of the tests, of course, have different limitations, but most of them have similar null hypothesis and very similar steps in most cases. And again, as in the problem with multicollinearity, there are no unique rule, no unique approach for detecting heteroscedasticity. And in most cases, I want to repeat again this general idea that heteroscedasticity may be a matter of intuition or some educated guesswork, or if you have prior empirical experience. So all these um, formal methods plus your intuition could help you to detect and solve the problem of heteroscedasticity as well as the problem of multicollinearity, okay? And also I want to remind you that of course we talk about the error term when we talk about the heteroscedasticity, but we cannot obtain the error, the some estimators of error term, yeah, because error term is unobserved. But instead of this, we again use the residuals. So all the tests, all the techniques for detecting the heteroscedasticity based on the residuals. So the question for you, which method could we use for detecting the heteroscedasticity? What do you remember from the seminar in Stata?
Maybe after regression, we can simply predict values and then extract observed minus expected. And then we can analyze our disturbance.
Okay, you obtained residuals, and how can you analyze maybe some special tests, some special techniques? So
First,
you
we
need,
can plot it, and then
yeah.
we can check for skewness and kurtosis for normality checking.
Okay, skewness kurtosis. This is the techniques to detect normality. Just a second, sorry. Again, some. Yeah, Елизавета, thank you. RVF plot, for example. Yeah, this is some informal method. How can we detect the heteroscedasticity? And again, let return to our conversation about the skewness and kurtosis. Skewness kurtosis is about the distribution, about the normality or approximate normality or not normality distribution of our variables. When we talk about the heteroscedasticity, we need to take a look at the residuals, not only on the normality of the distribution of these residuals. We need to find some patterns. So let's discuss the first informal method. Again, we should take a look at the nature of the problem. So very often the nature of the problem under consideration suggests whether heteroscedasticity is likely to be encountered or not. For example, if you, let's say, read some article with very similar model and the similar data set, yeah, for example, based on some respondents, and you are interested in the income of households, and you know that you include different sizes of households who, let's say, has very high income and very low income, and you combine all these households in your sample, of course, you can assume that the heteroscedasticity problem will arise in your model. But also, the second informal method, you can use graphical methods. For example, you can use plot of residual versus fitted values, or versus not fitted values versus some explanatory variables. You can choose which one, and you can take a look at the plot of the residuals, for example, versus the variable of your main interest. Okay, and the idea being to find behind the graphical method is whether the estimated mean value of your dependent variable is systematically related to the residuals, in some cases to the squared residual. It depends on the graph that you use. So exactly, if you type area of plot, as Yelizaveta suggested in our chat, you will see such kind of picture as you can see in this slide. So residuals versus some fitted values, some predictions. So let's say that we obtain such kind of picture, and what conclusion can you make if you take a look at this picture about the heteroscedasticity or homoscedasticity? What can you say?
Well, we have heteroscedasticity because our residuals are distribution are not equal to each other, variances of them.
Yes, Konstantin, you're right. So in this case, you can see some pattern. Yeah, you can see that the residual become higher in the higher values of your fitted of your predictions of your dependent variables. Yeah. So this is one of the example how heteroscedasticity can looks like. Okay, but additional to some informal methods, of course, we can use the formal methods. And formal methods, we can run some simple tests that can help us to detect the presence of heteroscedasticity. And as usual, we should run with the linear model. And when we run with the linear model, we should assume that we obtain unbiased and consistent coefficients. And first of all, we need to formulate the null hypothesis. And the null hypothesis in all these tests that you have a homoscedasticity. So we take the null hypothesis that homoscedasticity assumption is true. And the variance in the error term conditional on your independent variables is the same. So if you want to really understand the main idea behind this test, it's better to rewrite this equation through the expected value. So you can rewrite this mathematically through the expected value and say that assuming the zero conditional mean assumption, you can say that the variance in this case equals the expected value of squared error term, conditional again, of course, on the same independent variables. And also you can say that this is equals the expected value of your squared error equals some positive constant term. And this constant term, of course, unrelated to your axis. So in general, this implies that under null hypothesis, the squared residuals should also be unrelated to the explanatory variables. And this idea is the same as you can find here. Okay, and now let's start with the general idea of two popular tests. The first one is Breusch-Pagan and the second one is Y-test. So the null hypothesis that the error variance are equal, or the null hypothesis is that we have homoscedasticity in our model. So if we cannot reject this null hypothesis, it will be good for us, yeah? We can assume that we don't have the problem of heteroscedasticity if we cannot reject the null hypothesis. This is our desired property of ordinal least squares estimators. But unfortunately, if we has a very small p-value, in this case, we should reject the null hypothesis and we should conclude that we have the problem of heteroscedasticity. Okay, so we need to obtain some statistic and we need to obtain and calculate the p-value and compare p-value with the significance level. In most cases, we choose, of course, 5% significance level traditionally. So let's take a look at the steps. How can we conduct? Let's start with the Breusch-Pagan test. So let's start with the details. In the first step, you run the model by ordinal least square approach as usual. From this model, you obtain the residuals. Here you can find this. And after we obtain the residuals, in the second step, we can take, first of all, we should square these residuals, and then we can take these residuals at the dependent variable on the same independent variables on the same axis. So our regression, our auxiliary additional regression, will look like this. Here's the squared residuals, and this on the right side in this equation, you can notice the same explanatory variables as in the previous step. Why do we need this regression? Because we want to obtain the R-squared indicator in this regression. So then we keep the R-squared from this regression and test the null hypothesis that all these coefficients equals 0. And the dependent variable, I want to remind you one more time again, here is the residuals, yeah? Because of this, we can conclude after this with the special statistic something about the R-squared. And after this, we can use F statistic or Guérin's multiplier statistic and compute the p-value. So if the p-value will be sufficiently small, you reject the null hypothesis about the homoscedasticity and you conclude that you have the problem of heteroscedasticity, and in the next step you should solve this problem using some techniques we discuss, what kind of techniques you can use to solve this problem. Okay, so Breusch-Pagan test suggests a different form of the test that assume the errors are normally distributed. And you can check the help guide in Stata, for example, or in some other software packages to find the special options that you can add to the Breusch-Pagan test. And for example, you can eliminate the normality assumption of your residuals, because the original Breusch-Pagan test that you run by the default in Stata assume that you have normally distributed residuals. If you want, for example, to eliminate this assumption, you can add special options. Please check all the options in the Stata, or please ask to do this during the seminars with your teachers, okay? Because every time when you start to work with the new tests, first of all, you need to check all the assumptions of these tests, because these tests, this assumption of this test influence your conclusions and influence the limitations of this test, okay? So one more test that we are going to discuss is white test. The idea is very similar to the idea that we just discussed in the Breusch-Pagan test. But White proposed a test for heteroscedasticity that adds the squares and cross products of all the independent variables to the equation. So the first step in the test is absolutely the same as we just discussed. You just run the your, let's say, original regression, yeah, of y on all axes. And again, you obtain the residuals. But in the second step, again, you use the same dependent variable, but you add all these square terms of your dependent variables, as well as the cross products between the independent variables in your model. Why it's important? Because in this test, in this test, you can check only the linear form of heteroscedasticity. But of course, the heteroscedasticity could have not only linear form, yeah, it could have some other different forms. And if we want to check this, white test can provide you with such opportunity. But here you can see that we add 9 restrictions, and all these 9 restrictions, 9, I mean, because you have here 9 variables, yeah, your original variables, then the square terms and the cross products. Now you test 9 restrictions in this example. And again, you obtain R squared and use F statistic or Lagrange multiplier statistic and compute the p-value. Yeah. If you have question about F statistic or Lagrange multiplier statistic, the formula, you can check the previous lecture and find the formula where you can find how to estimate F statistic through the R squared indicators. We discussed this previous time. Okay, so the main disadvantage of y-test that even if you have let's say 3 independent variables, like in this case we have 3 x's here, even in this case the equation in the second step here has 9 independent variables, and this is real weakness in the pure form of the y-test, because it uses many degrees of freedom. for models with just a moderate number of independent variables. Let's say that you have here not 3, but let's say 9 independent variables, and your sample is not very large. Let's say you have only even 100 of observations. In this case, you decrease the degrees of freedom, and it's not very good, of course, for the precision of your estimators. And because of this, you can run the special case y-test. The first step here is absolutely the same, but in the second step, you add the square term of fitted values that you obtained in the previous step as the independent variable. And if you square the fitted values, you get a particular function of all the squares and cross products of the independent variables. And after this, you again can just run the F statistic or Lagrange multiplier statistic. It depends on the approach that used in the software packages. Okay, so let's summarize our ideas about the testing of heteroscedasticity. Of course, the first idea that you have a lot of different tests. We just discussed 2 of them, Breusch-Pagan and y-test, and also you used the same test for detecting the heteroscedasticity presence in your model when you work in state in your seminars. But you can find more different tests, more that you can use for detecting the heteroscedasticity. But even if you compare 2 of them, the y-test may detect more general forms of heteroscedasticity than the Breusch-Pagan test. And in fact, the y-test is extremely general. This test can check different forms of heteroscedasticity. But the test may reveal heteroscedasticity, but it also may detect heteroscedasticity, instead simply identify some of the other specification errors. For example, incorrect functional form, the problem that we discussed. So first of all, before you run any tests, before you run any approach to detect the heteroscedasticity, please be sure that you have the correct functional form of your model. This is the first step, okay? Because all of the tests could be very sensitive to the form of your model, and maybe you can obtain that you have the heteroscedasticity problem, but in reality this just be the some misspecification error, okay? And also you should remember the power of the y-test may be rather low if you have the small sample size because of the number of restrictions in the general form of this test. So how can we solve the problem? Okay, we detect that we have the problem of heteroscedasticity, but now we need to solve this problem. And again, let's continue our discussion about the specification of our model. And of course, this point should be the first here, not the last one. If we take a look at these points as the some order, yeah. But also you can change the method of your, for example, instead of ordinal least squares approach, you can use generalized least squares method or weighted least squares method to find their coefficients. And these both methods were very popular before we can before the econometricians, before the empirical researchers find how we can solve the problem of heteroskedasticity when we just change the standard errors of our coefficients. Because you still can find some papers where some authors try to solve the problem of heteroskedasticity with generalized least squares method or weighted least squares method, but these methods are not very popular nowadays because we can just use robust standard errors. And to find the robust standard errors and to use them in our statistics when we test the hypothesis about the significance of our coefficient is nowadays the most popular and the most robust method, especially in large sample size. So how can we do this? Instead, you can just add the robust option or cluster ID option after the regress command. Yeah, I hope that you remember this. So, and it could be relatively easily solved in this case. So now let's take a look at the theory, how it looks like. So in the general multiple regression model, we can write this model in like following. And you need to, let's say, re-estimate. You need to change your standard errors. So because of this, you need to find the new variance of your estimator, of your parameter. And for this purpose, you can write this formula. This formula looks very similar as we discussed in the previous seminar. Yeah, we take a look at the formula of coefficient variance in the multiple regression model. But here you add the residuals from the regression x on all other independent variables, and in the denominator you can see the sum of squared residuals from the regression again of x variable on other independent variables. And the square root of this quantity is called the heteroskedasticity robust standard errors. So sometimes in some packages, the degrees of freedom could be used at the correction to this formula. So here you can add the degrees of freedom, and also you can rewrite the sum of squared residuals at the total sum of squares and the R squared indicator. We discussed this formula previous time. So this is the formula. How can you estimate the heteroskedasticity robust inference through the heteroskedasticity robust variance and robust standard error? And that's all. So let's summarize this topic. First of all, if you check and find that you have a heteroskedasticity problem, even in this case, your coefficient could still be unbiased and consistent. But you just need to change the standard errors of your coefficient to run the hypothesis tests and to check the significance of your coefficient to find the partial effects of your coefficients, okay? And you can use this formula to do this. This is the most popular way, or you can just change the approach that you use. For example, instead of ordinary squares method, you can use generalized squares method. But of course, this method also has some limitation and some discussion. So generally speaking, just change the standard errors. This approach is very, this is the general approach, especially for large sample size. But also you should remember that one reason the usual standard errors are still could be preferable in cross-sectional work is that if the homoscedasticity assumption holds and the errors are normally distributed in small sample size, the usual t-statistics have exact t-distribution regardless of the sample size. And with the small sample size, the robust t-statistic can have distributions that are not very close to the real t-distribution, and that could throw off your conclusions and throw off your inference and conclusion about the statistical significance. But in large sample size, we can make a case for always reporting only the heteroscedasticity, robust inference in cross-sectional applications, and that's all. But as your students, and this is your first steps in the empirical research, anyway, please check the heteroscedasticity problem that this problem present in your model, and only after this decide should you use robust standard errors or not, especially in small sample sizes. Okay, now we have 20 minutes left, and let's discuss an interesting topic about how can we combine some variables in our model. So we can use interaction term is an independent variable in regression equation. And this interaction term presents the product of two or sometimes even more than two independent variables. It's interesting topic because in this case you can check some interesting hypothesis about the relationship between the dependent and independent variables, and you can take into account one more independent variable, for example, when you check the relationship. So you can divide the effect in different groups. So in this case, your interaction term has its own regression coefficient, but let's discuss how it looks like. Generally speaking, you can face several interaction terms. For example, let's start with the easiest one, where we want to combine two dummy variables. And imagine that you have some sample and you want to check the difference of return to self-employment between genders, between males and females. So you want to assess such kind of model where the dependent variable is the income, and you have several explanatory variables as the dummy variables. The first one here, D1, is the first dummy variable, presents 1. This the category of this variable equals 1 when the respondent is male, and 0 otherwise. And the second dummy variable here is the self-employed status that equals 1 when the respondent is self-employed, and otherwise equals 0 when, let's say, the respondent is paid worker. And also we want to check if the self-employed status gives some premium that depend on the gender. So when we add here the cross product of these two dummy variables, we just want to check this equation is just a way of, let's say, finding income differences across all gender status, working status, I mean, combinations. So how can you understand this equation? For example, let's say that we want to assess this equation only when our respondent is female who is paid worker. In this case, these two dummies, the first dummy equals 0 and the second dummy also equals 0, yeah, because female category females equals 0 and category of paid workers also equals 0. And in this case, you keep only the first intercept, this one, yeah, because all other terms equals 0. And if you take that d, now the second dummy variable equals 1 and the first one equals 0, you can find the difference in income between self-employed females and the base group. In our case, the base group is females who are paid workers, the base group that we just discussed here, yeah? So the difference will be presented here in the beta 2 coefficient. So it's beta 2, or if you want to predict the average effect of your dependent variable, you can just summarize beta 0 plus beta 2 and so on. For example, if you want to find the difference in income between self-employed males and again, the base group females who are paid workers. In this case, you should add which intercept, beta 0 plus beta 1 plus beta 2 and also plus beta 3. Yeah, because all these dummies equals 1 in this case. So generally speaking, when you add this cross product of two dummies in your model, these dummy variables just captures a shift in the intercept as the result of some qualitative factor is an intercept dummy variable. So you can see the difference just at the shift across your vertical line, across your dependent variable, yeah? You can imagine this situation. So the most popular cross-product interaction when you interact one dummy with one continuous variable. So let's continue the same example where your dependent variable is income and your independent variable, the first one is self-employed. Dummy, yeah, the same, self-employed or paid worker. And the second independent variable, instead of gender, let's use the education, but indication in years. So this is the continuous random variable. And here the important hypothesis that the return to education is not the same for paid workers and self-employed respondents. So the main hypothesis that we will see the difference in the return to education in income, how education affect self-employed and how education affect paid workers. There will be the difference between these two groups. And if we want to check this hypothesis, we need to add the cross product um, here, and the beta-free coefficient will describe if there is really exists this difference, if there is really exists, let's say, this premium of education that that is different for different um, working status. So if we plug that working status equals 0 into the model, then we find that the intercept for paid workers and the slope on education for paid workers. Let's say that this equals 0, this term also equals 0, and you obtain only that the intercept for paid workers equals beta 1. Oh, sorry, the intercept for paid workers equals beta 0, of course, and the slope for paid workers equals beta 1. But for people, for respondents who are self-employed, it means that the dummy variable equals 1. And if you implement this in the model, you can see that for this group of people, the intercept equals beta 0 plus beta 2, and the slope equals beta 1 and beta 3. Yeah. So let's take a look at the graph. How can we present this idea in the graph? So this is our estimated, this is our proposed model that we want to assess. You can see two different lines here. It looks like you estimate two different equations, yeah? Because the slope, you can see that the slopes are different in these two different groups, as well as the intercept for these two groups will be different. So the slope dummy and intercept dummy terms are added to an equation will lead to different intercept and different slopes. And the difference between the two intercept here is beta 2. This is the difference. And whereas the difference between the two slopes is beta 3. Okay? So, generally speaking, again, if you want to check such kind of hypothesis that, for example, in two groups or more than two groups, also you can add here some categorical variables instead of dummy variables, dummy. But the dummy and the cross product of dummy and continuous variable is the most popular approach when we want to find the effect of some continuous variable on your dependent variable, if this effect will be different in this in different in two different groups, is more the popular approach. Okay, so I know that you will practice how to implement these models and how to interpret the coefficient of these models, and also how to write the estimated equations for such kind of models when you have the interaction terms next week. So I hope that everything will be clear for you in this topic. And now let's discuss your questions.